Welcome back. So here we have an internal combustion engine, and now our job is to find the length of this connecting rod between this crankshaft and this blue piston here. And so here I can show it to you in slow motion. And so essentially we need to find the length between this red dot and then the middle of this blue piston. Of course, since we are learning about vectors, I want you to use vector concepts to find that length. And in order to do that, I need to give you some initial conditions. So essentially, what we need to do, we need to freeze this engine at some point and then give some initial conditions or initial dimensions to find the length of this connecting rod. And I'm going to do it like this. You have x in millimeters, y in millimeters. You have your blue piston here. Then this red dot on the crankshaft, it's here. And so this purple line, that's the connecting rod. And so the information that I'm going to give you is the following. This red dot, it circles like this. And so the center of the rotation, it's this point here. It's the origin of this coordinate frame. So you see you have this rotation circle, and the radius of this rotation circle is 1 to 5 millimeters. And so when I freeze this engine, then at the time when I freeze it, this angle here is 25 degrees. And then the horizontal distance from the center of the rotation till the center of this piston is 400 millimeters. So all these numbers here, they are in millimeters. And so using this information, you have to find the length of this purple line. Let's call this point A, and let's call this point B. It turns out that there is an easy way to do it. Let's say that I have an XYZ coordinate frame. And in that frame, I have a point in space called P. I can represent the position of that point with a vector. I call this vector RP. This vector can be constructed with the three XYZ components, RPX, RPY, and RPZ. And this vector RP, it's called a position vector. It makes sense because it describes the position of something. The tail of that vector comes from the origin of the coordinate frame, and the head of that vector is where the point P is. But now let's define another point, and let's call it S. We draw another vector that goes from the origin of the coordinate frame till the point S. We call this vector RS. Again, we can construct this vector using three components. RSX, which is this arrow here, RSY, which is this arrow here, and RSZ, which is this vertical arrow here. So we can say that RP vector equals RPX times I plus RPY times J plus RPZ times K. And then RS vector equals RSX times I plus RSY times J plus RSZ times K. And finally, I will draw another vector from S to P, and I call it R, then P slash S. It means P with respect to S. So S is the origin for this particular vector, and P is where the vector is headed. That's why it's P with respect to S. This is one notation, which I will be using a lot. Another notation that you can use is this one, R and then SP, but without this slash sign. It would mean that you go from S to P, but with the slash sign, it means P with respect to S. If instead of going from S to P, I would go from P to S, so now the origin is P and now the vector is headed towards S, then instead of this notation, I would write rs slash p, so s with respect to p, or alternatively, I would write rps, so from p to s. However, in our case, we go from s to p. And now you can also say that rp vector equals rs vector plus rp slash s vector. It makes sense, right? I mean, that's how you add vectors. You put the tail of this purple vector where the head of rs is, and then you get rp, which is essentially your resultant vector. But then you can also say that rp with respect to s equals rp minus rs. It means that this vector here, it's really the difference of these two vectors. It's the difference of rp and rs. And so if we now use the I, j, and k components, then rp slash s equals, this is the rp vector minus, this is the rs vector, and so all that equals I times rpx minus rsx plus j times rpy minus rsy plus k times rpz minus rsz. And so this vector here, it's called a displacement vector. So the difference of two position vectors is a displacement vector. It's different from distance though. Distance is a scalar quantity. It just tells you how long something is. It has no direction. But displacement is a vector. It has a direction. In our case, its direction is from point S to point P. If you divide the displacement vector magnitude by the change of time, or delta t, then you get the average velocity vector magnitude. So delta t is the time that you need to go from S to P. So if here you are at t0 and here you are at t1, then delta t would be t1 minus t0. And the average velocity vector that you get has the same direction like the displacement vector. So velocity is a vector. But remember, velocity does not equal speed. Speed is a scalar quantity and velocity is a vector quantity. Speed simply shows you how fast you cover distance, which is also a scalar. So distance over delta t equals average speed. And the reason why I say that speed and velocity are average is because I'm not assuming that this delta t is infinitesimally small. Maybe it takes you 40 seconds to go from S to P. During that time, your speed might vary. Sometimes you might go faster, sometimes you might go slower. So that's why I say average velocity and average speed. But okay, let's go back to our displacement vector. By taking the difference of rp and rs, you have essentially created a new coordinate frame. The origin of this new coordinate frame is this S point. And here you also have three axes, x apostrophe, y apostrophe, and z apostrophe. Note that x apostrophe is parallel to x, y apostrophe is parallel to y, and z apostrophe is parallel to z. You haven't rotated this new frame with respect to the old one in any way. You have simply shifted the coordinate frame in such a way that the origin of it is now where the point S is. And from that new origin, I draw my displacement vector, rp slash s. And so from this new coordinate frame, we can construct this displacement vector like this. This component here, that's in the x apostrophe direction, and it's this one here, rpx minus rsx. Then this component, that's in the y apostrophe direction, and it's this one here, RPY minus RSY. And then this component that goes vertically down, that's in the Z apostrophe direction, and its magnitude is this one, RPZ minus RSZ. So this X component has a positive X apostrophe direction. This Y component has a positive Y apostrophe direction. And then this Z component that you have here, that's in the negative Z apostrophe direction. Note that if instead of RP minus RS, I had RS vector minus RP vector, so I would have RS with respect to P, then my new coordinate frame would have been shifted here. Its origin would be the point P, but again, X apostrophe, Y apostrophe, and Z apostrophe, they would be in the X, Y, and Z direction. So by taking this difference, you only shift coordinate frames, you don't change their orientation. And so your displacement vector would be this one then, your RS slash P, and then your X apostrophe component, it would be this one, then your Y apostrophe component would be this one here, and Z apostrophe component, it would be here pointing up. Note that all these three components, they have the opposite directions to what you had here. So if here you had RPX minus RSX, then here you would have RSX minus RPX. It would be this one here. Then here you have RPZ minus RSZ. Then here you would have RSZ minus RPZ. And then here you had RPY minus RSY. Here you have RSY minus RPY, which is this one here. So all the components of the displacement vector from the new coordinate frame would have the same magnitudes, but they would be opposite in direction. And it makes sense because now you don't have RP minus RS. You have RS minus RP. However, our case was RP minus RS. This was our case. So let's stick with that. And now what you can do, you can take your displacement vector and you can calculate its magnitude. So the magnitude of your displacement vector, or I will simply write it like this, it equals RPX minus RSX squared plus RPY minus RSY squared plus RPZ minus RSZ squared. And then I'm going to take all that to the power of 1/2, which is essentially taking the square root of everything here. And so this magnitude here, it will give you the length of this displacement vector arrow. In other words, it will give you this straight line distance from point S to point P. And using this concept of finding the length of your displacement vector, using that, you can solve this engine exercise. Now you can calculate the length of this connecting rod knowing the initial data that you have here. So try it out by yourself first, challenge yourself, try to calculate the length of this connecting rod using this concept here that we have just discussed, and then see my solutions in the next video. Thank you very much. Welcome back. So let's now calculate the length of this connecting rod using the vector principles that we discussed in the previous videos. We know that the center of rotation of this point A is here in the origin of this coordinate frame. So let's call this origin O. And so how about I define a position vector from the origin till A, and I call this position vector A with respect to O, or simply A, and you know that the magnitude of this position vector is 125 millimeters, and you have this angle here, 25 degrees, so you would agree that the x component of this position vector would be the following: minus 125 times sine 25 degrees times I. It's minus because it points in the negative x direction. And then you will have plus 125 times cosine 25 degrees times j. It's positive because it points in the positive y direction. And then to be complete, I could also write plus 0 times k. Since we have a two-dimensional problem right now, we don't have a third dimension, which means that you have 0 millimeters in the k direction. But if you had a three-dimensional problem, then you would have another number here. And then we can define another position vector, this one here, and we can call it RB with respect to O, or simply RB. And so it would be 400 times I plus 0j plus 0k. And of course, both position vectors are in millimeters. And now what happens if I write RB minus RA? Well, you will get a displacement vector, RB, with respect to A. So your displacement vector would start from point A and it will go till point B along your connecting rod. So RB with respect to A equals I times 400 minus 125 times sine 25 degrees, then plus j times 0 minus 125 times cosine 25 degrees, and plus k times 0 minus 0. So your displacement vector equals 452.8i minus 113 times j plus 0k. So essentially, like we discussed before, by taking this difference, you have shifted your coordinate frame. This one here, that's your x apostrophe. Then this one here, that's your y apostrophe. You can see that you have only shifted this coordinate frame. You haven't rotated it. X apostrophe still points in the x direction. Y apostrophe still points in the y direction. And so this component from here, from the origin of this new coordinate frame, it's this one here, 452.8 millimeters. And then this component here that points down, it's this one, minus 113 millimeters. So it's this component here. It points in the negative y apostrophe direction. And well, at the moment we don't have to worry about our third dimension. But again, if you had a three-dimensional problem, then instead of these zeros, you would have other numbers. That's why I'm including this third dimension in order to give you a structure for a general three-dimensional problem. And so the magnitude of this displacement vector is 452.8 squared plus 113 squared plus 0 squared, and you take the square root of it, and you will get 467 millimeters. And there you go. The length of your connecting rod is 467 millimeters. So when you go from this red point till the middle of this piston, then this connecting rod, its length is 467 millimeters. And as you can see, it was very easy to find using these vector concepts. Thank you very much.